Good day, welcome to the section on horizontal alignment. To best illustrate this example here, we are going to be using a practical example. You are given a brief where you're given an annexure, a layout showing a plan view, showing a section of mapping which has been prepared for realignment of section of a provincial main road. There have been a number of accidents on the curve across the stream, and the authorities have decided to realign the road to a design speed of 80 kilometers per hour. You have been given a copy of the plan and must develop your own solution to the problem as we work through the example. So this is a layout that has been given to you. We'll look at this layout in more detail briefly. Your design should make provision for the following: a realigned horizontal alignment. The road is to have 3 meter length and 1 meter shoulders, and the design 1 meter shoulders, and the distance to the shoulder break point is 1 meters. You're also required to do a vertical alignment, and you also required to do an axis. Those two will be in future videos. At this stage, we're concentrating on the realignment of the horizontal alignment. And remember, your road has to have 3 meter length and 1 meter shoulders, and the distance to the shoulder break point is 1 meter. Your proposal should clearly indicate on the annexures provided and should be supported by all necessary calculations. Let us first examine the plan which has been provided. So you were given the layout. A couple of things that you have to know. This is the problem. There's a stream running here and there's been a lot of accidents here. And therefore realignment is required. Right? If you look on this road over here, we can start guessing how many curves there are, and generally we get answers in the range of 7 to 11 curves. However, there are 14 different radii on this curve because there are some curves that are compound, so there's quite a few curves along this. You can see one curve there, one curve there, one curve there, another curve there, another curve there. So right through, there are about 14 different radii here. If we just suggest that we realign the road such that there are only 2 curves, would you think this is possible? Let's start examining this. A scale has been given to you and you have in front of you grid intervals, right? Just if we had to zoom in here a little bit. Right, 3382 200, and if I have to go slightly up, that's 40, 200, right? Also, you have to take cognizance of the fact is how is the ground, the terrain of the ground. And if you look over here, you got your contour intervals. They are 2 meters apart. So you got 32, 34, 36, 38, 40. So those are your contour intervals over here. So you have to take cognizance of that as well. Right, so look at your scales, double check your drawing that it is to scale, especially when they have grids. Don't ask me what the scale is. If the scale has been given to you, please, it's your responsibility to check that things are to scale based on grids, right? Be aware of the contours and how the ground is falling, the terrain of the layout, right? And you have to, the scale is important, the grid is important at this stage. Moving on. This is a flow chart to do a horizontal alignment. I'm not going to go too much into detail of it because as you progress, you'll see we're following this path here. And the design speed has been given to you at 80 kilometers per hour. Is the radius of the curve is given? In our case, it's not given, so we're going to take this route over here. If it's given, you're going to take this route over here. Some of the formulas that you would use is, I'm not going to go through that because we'll see it in our calculations. Right, so you can get your formulas from the data sheets here, or there's a data sheet with a whole lot of formulas which is also on Moodle, and you can look at that as well. Determine the minimum permissible curve radius. Irrespective of whether we design a circular curve or a transition curve, the first thing we need to determine is what is the minimum horizontal curve radius that we need to use for a design speed of 80 kilometers per hour, which was given to us. The standard equation is E plus F is equal to V squared divided by RG. F is equal to 0.19 minus V divided by 1600, 0.19 minus V 80 kilometers per hour divided by 1600 is 0.14, which is your friction. Now substituting this in the standard equation and solving for R, we get from this equation over here, if we had to make R the subject of the formula, R is equal to V squared over E, which is a super elevation, plus F, which is your friction, right, times your G, which is 9.81. Notice over here for V, in this formula here, you should be quite familiar with this, that we don't look at it as 80 kilometers per hour. We convert it to meters per second by multiplying it by 0.278, which is the standard. So 80 times 0.278 or squared, your V squared, divided by your E, your super elevation, is we're looking at it as being 10%, which is a standard maximum, plus 0.14, which we just calculated above there, times 9.81, giving you a radius of 210.082 meters. So provided we use a curve radius greater than 210.082, we will be able to comply with geometric design standards that have been set. For the purposes of this calculation, we would choose a radius of 250. Right, so the minimum we calculated was 210, and generally we do up the minimum to in intervals of 50, so therefore we're using 250 meters. So what we're going to do now is that this layout was given to us. We're going to take two straights, as you see in this line over here. So here's your PI1, here's your PI2, and your PI3 somewhere there. We'll discuss those just now. Determining of your, based on your design speeds, these are the standards that generally use of the minimum curve radius based on your super elevation, and those values have been given over here. There's approximately 140 kilometers, there's approximately 140 meters from the kilometer post to the start of the alignment, right? How do we know this? Because we took a scale rule and we measured. So we're looking at about 140 meters from the kilometer post to the start of the alignment. So this is something that we scaled off from the plan. Right. So there's your 12 kilometers over there, and what we did is we measured off the 140. Right. We are now able to scale off the X and Y coordinates for the points of intersection of our horizontal alignment using the coordinate information given on the map. So you had those grids over there, so now you can scale off the beginning, the PI, and the end, because you know from the grids wherever they sit, you can get a coordinate here easily based on the grids that you already have and scaling of distances. So you can pick up coordinates like that. We can now calculate the direction and distance from beginning to PI and PI to end using the join calculation. So if you've got coordinates to get from to get a distance and direction between these 2 points, you use joins and polars, and that can easily be done. From PI to end, you can work out that as well. As you are unlikely to remember how to calculate join as required in this case, or a polar, a revision sheet for each has been provided in your course notes. You will also use a programmable calculator to do this calculation. So to work out joins and polars, we're giving you the supported documentation to just recap your memory, and you can look at that in your own time. We are now able to scale off the x and y coordinates for the points of intersection of the horizontal alignment using the coordinate information given in the plan. So the beginning y coordinate is 4022.50. The x coordinates there at 42.50. That's the beginning, 3382.155.00. Right? These are the distance that you scaled off. The PI point coordinate is there and the end coordinate is there. Based on this, during your joins and your polars, you can work out from beginning to PI. The direction is 123, 34, 33. Distance is 141.033. PI to end, direction you've calculated to be 81 degrees at 8 minutes 3 seconds. This distance is 171.828. The intersection angle is 41.56.35. Just a quick over here. So there's your PI1, right? There's your PI2, there's your PI3, right? So basically what you're doing over there, after you've got your grid values, you've calculated the distance from PI1 to PI2 as been 141.033, and you calculated the direction to be 123 degrees 34 minutes 38 seconds. From PI2 to PI3, you calculated the direction to be 81 degrees 38 minutes 3 seconds, and the distance is what you calculated, 171.828. Right? So that's basically what we did from start to PI1 to PI2. We can now determine the intersection of the angles. So you take both these angles, subtract it from each other, you get an intersection angle of 41 degrees 56 minutes and 35 seconds. So effectively what we're looking at is this angle over here. So taking that direction minus that direction, and that's when we get this angle over here. So the intersection angle is pretty straightforward. Now we can move on to calculate the tangent length. In terms of the formula for horizontal alignment, the tangent length is given by r times tan theta over 2. We calculated r in a previous slide, minimum r, and we said we're going to be using 2 to 50 multiplied by tan, and theta over 2, right? We just calculated theta to be 41 degrees 56 minutes and 35 seconds. We divide that by 2. We get a tangent length of 95.823. So what's 95.823? 95.823 is a tangent length, which means it's the distance from the PI to the BCC. Right? So that's the 95.823 that we calculated. We can now determine the SKD of the BCC of the circular curve. Taking 141.033 and subtracting the tangent length, we can now determine the distance of the BCC1, and that is equal to 45.210. Therefore, SKD for the BCC is 1860 plus 45.210. Right? So if we calculated that to be 95, this is simply, remember the 141, so it's simply that minus that will give you your 45.120, right? So if you've got that SKD, right, you can work out the SKD there as well. Right? You've got the SKD of the PI, now you can work out the SKD of the BCC1. Now we need to calculate the SKD of the ECC1. So if we know the SKD of the BCC1, and if we know this curve length over here, won't we get the SKD of the ECC? So at the moment what we're going to do is we're calculating the length of this curve over here. Right? So the curve length is given by r theta, and theta is in radians. You know the radius already. All you have to do is your theta. To convert that to radians, you have to multiply by pi over 180. And then you get a crown length of 183.01111. So all you're doing is your BCC, which you just calculated. You're adding on your curve length and you're getting your ECC. Thank you.